Great. You're ready to start?
Yes. Okay. Yeah, so today, as mentioned, we're going to talk about something completely different, which is an introduction to infinity categories. And this will form the basis for some of the next talks that are going to come in the workshop. And of course, it won't be feasible to give a completely fully detailed introduction to infinity categories. So my aim is to give you an overview, a flavor of how this theory is supposed to work. And hopefully give you concrete enough guidance so that you sort of have an idea of how it works. Today we will start with a general introduction of infinity categories, and then tomorrow we'll talk about stable and symmetric monodal infinity categories. Okay, and by the way, if there are any questions, feel free to interrupt. I guess maybe you can ask them in the chat also. I don't know precisely what the best way is. Let's start with a motto for what higher category theory is supposed to be. So I like to think of it as a combination of category theory, as we're used to, together with homotopy theory. I will explain in a second how I interpret the phrase homotopy theory. But the main thing I want to make clear is that sometimes people get a bit confused and they think, oh, infinity categories, it's a generalization of two category theory with two categories, three categories, and so on. And we have all these higher morphisms. And this is in some sense a little bit correct, but it's in some sense also not quite the right intuition. I really want to think of infinity categories as sort of, they're also called infinity one categories. It's really usual category theory, except that all the things you do are now up to homotopy. Yeah, so let me explain a little bit more what I mean by this phrase homotopy, because I have sort of something a little bit more specific in mind, which I like to call the fundamental principle of homotopy theory. I think a large part of getting familiar with infinity categories is really understanding this fundamental principle of homotopy theory that I'm going to write down in a second, which says the following. Whenever we want to express that two mathematical objects that we encounter are equal, usually it's a yes or no question. The things are equal or are not equal. And in homotopy theory, we want to get rid of this binary notion of equality. We want to think of it as structure. So we want to say, how are they equal? So by providing some data, an isomorphism or a homotopy between them. So in other words, equality is structure, not a binary yes or no question. And if you really understand this principle and take it seriously, and then you start just doing category theory, then what you end up with is basically higher category theory. So this is sort of the most fundamental thing to understand. And let me say a bit more about what I sort of mean by this. So we are already very familiar with this concept if we're talking about mathematical objects. So for example, if I wanted to say that two groups are equal, usually you don't really mean that the groups are literally equal as sets. What you very often just means that there is an isomorphism between G and H. And you remember the isomorphism, and whenever you have a statement about G, it's also going to be true for H. Or maybe, you want to talk about homotopy equivalences. And then whenever we have something about the homotopy type of X, it's also going to be true about the homotopy type of Y. Or maybe, yeah. But the point about homotopy theory is that we apply this principle also to, for example, morphisms. So usually in group theory, we wouldn't really say, like F, a map between groups is just equal to F, it's just a yes or no question. But in homotopy theory, we sort of apply this principle also to morphisms. So for example, if we have two continuous maps, F and G from X to Y, then we want to think of them as sort of equal, homotopically equal, if there is some homotopy between them. And we often just want to remember the data of the homotopy. Okay. And then, you even go on and you have homotopies between higher homotopies and so on and so on. Whenever you want to say equal, you have to replace it by some type of homotopy. So if we take this seriously, let's think about what this means for our category theory. So what should a higher category be? So we should have objects as in an ordinary category. We should have morphisms. But then to talk about equality of morphisms, we need a notion of homotopy between them. And to talk about equality of homotopies, we need to talk about we need to have some notion of homotopies between homotopies. And this process continues up to infinity. And this is sort of, I guess, the reason why these infinity categories are called infinity categories. So, yeah. A question you might have at this point is, okay, how do you make this precise? This notion of an infinity category, this vague idea that I described. And I think I would like to avoid giving very precise definitions. Like I mean, for most of the talk, I will try to describe the theory of infinity categories without relying very much on any specific model. But I would just want to briefly mention some of the options. So so if you would like to really rigorously define, in terms of set theory, for example, what these objects are, one way to do this is using quasi-categories. You might have heard this phrase. This is sort of the common choice in the literature. Another thing you might have encountered is a notion called complete Segal spaces, and maybe a third one is simplistically enriched categories or Kahn-enriched categories. And yeah, the point I want to make is a little bit that focusing on these models is not really so relevant for understanding the general theory. It's much more relevant. How do you actually work with it once you have the theory? That is what I'm going to focus on in these two talks. But maybe, yeah, I think to give some illustration, I will give sort of idea of this second description of infinity categories, because it's the most helpful one, even from a model independent perspective. Okay, so let's define these objects. So the complete Segal space is a functor C. Okay, so maybe before I state the definition, I should sort of give some heuristics. So first of all, what we're gonna do is usually in a category we have a set of objects and a set of morphisms, and we're gonna replace these sets by topological spaces. So in a set, we can really talk about equality of objects. We don't really want that. So we're going to replace it by a space, and then we can talk about paths between objects. And that's our new notion of equality. But then also we need to encode all these higher homotopies somehow. So we're not just going to have a space of objects and a space of morphisms. We're also going to have sort of spaces. We have infinitely many spaces that we need. And they have certain relations between them, which we can encode by a simplicial object. So there is a category called delta. We'll call the objects and morphisms in a second. So the objects of this category delta are finite non-empty linear orders. So they are partially ordered sets of the following form. For some natural number n, we have the elements 0, 1 up to n. And each of these partially ordered sets is going to be sent to some topological space Cn. For n equals 0, this will be the space of objects. For n equals 1, this will be the space of morphisms. And then the morphisms in this category are going to be morphisms of partially ordered sets. So if we have some phi, which is a map of partial orders from n to m, then this is going to be sent, it's contravariant, so it's going to be sent to some phi upper star from Cm to Cn. I will draw out in a second how this sort of looks like in the low dimensions, but maybe let me first finish the definition by giving the two conditions that you need to impose. So the two conditions are the Segal condition, so such that one Segal condition the Segal condition should sort of say that this Cn is really the space of n composable morphisms up to homotopy. So for every I from 1 up to n, we can look at the sub-coset which only consists of the elements I minus 1 and I. And there is an inclusion of cosets into the partially ordered set bracket n. Yeah, maybe for convenience, let me assume that all these Cn's are just homotopy equivalent to some CW complex, so I don't need to worry about weak homotopy equivalence or homotopy equivalence. And then the condition is that all these maps EI induce an homotopy equivalence between Cn and the n-fold homotopy pullback of C1 over C0. Let me get back to this condition in a second to see why this is reasonable. But let me first state the second condition. Well, actually, let me wait for a second with the second condition and first sort of say why this is reasonable. So if we think of C0 as the space of objects, C1 as the space of morphisms, then this thing over here is really the space of n composable morphisms. So it's a collection of objects, x1 with the morphism f1, and so on and so forth, up to some fm and some object xm. And then the fact that Cn is equivalent to this now gives us a notion of composition. So, for example, we now have that C2 is equivalent to C1 times C0 over C1. So here we have some pair of X, F, Y, G, D, which corresponds to some object here in C2. But the advantage of C2 is that we can now have an additional map to C1. This is what we're going to call the composite of G and F. This map is induced by phi, where phi is the map from the partial order 1 to 2, which sends 0 to 0 and 1 to 2. So the upshot of this Segal condition, maybe it was a bit technical what I just described, but the upshot is that we still have a notion of composition in our Segal space, but it's no longer defined strictly, as in a category where you have only one choice of composite. It's sort of, the composite is defined up to homotopy, and associativity and unitality will hold also up to homotopy. Yeah. And in particular, because we can now compose morphisms, we can talk about isomorphisms in C. An isomorphism in C is a morphism F from X to Y that has an inverse. And it turns out to be convenient to ask for both a left and a right inverse independently. So we ask for a map. So when I write F from X to Y, what I mean is an element in C1 such that the source map sends it to X and the target map sends it to Y. Yeah, maybe I should have drawn the how this simplistic object looks like. So maybe let me do this here. So we have a C0, we have a C1, we have a C2, etc. And then what this diagram encodes is we have a source map which sends a morphism to its source. We have a target map which sends a morphism to its target. There's going to be a map from C0 to C1 which sends an object to the identity morphism. And then we have a bunch of other morphisms. So here, if we think of this as C1, like as pairs of morphisms with composable source and targets, then we have the projection map. We have another projection map to the second factor. We have the composition map, and then there are the inclusions that either put the identity on the second or the third. And then, the diagram has all these higher composition maps and so on and so forth. Anyway, yes.
So maybe there's one question in the chat, namely, do you work with actual topological spaces or some convenient category of topological spaces?
I work with some convenient category of topological spaces, but to be completely honest, the precise detail. So yeah, it's not going to be very relevant. So if you want to work very formally, then you should probably choose the model of quasi-categories. This is more to give you a heuristic, because once you know the whole theory of infinity categories, what you would probably do is put the infinity category of spaces here. So right now we cannot say that, but sort of in hindsight, you will look at this definition and you will see, okay, it makes sense also if I put the infinity category of spaces here, and that's sort of what I really have in mind. But this is not a formal definition. But I mean, this is the reason I give this definition as heuristic, because I think that even model independently, it's the most meaningful one. Yeah, I hope that addresses the question to some extent. Okay, yeah, so we get a notion of isomorphisms. F is an iso if there are a G and an H such that basically we want commutative triangles the following form. So what this means is an element of C2 whose first boundary is F, the second is G, and the third one is the image of this identity thing. And we want another two simplex which looks as follows. So you have Y and then H and then X and then Y again, and here we have F. So basically it says, this statement should be interpreted as GF is homotopic to the identity of X, and this statement should be interpreted as FH is homotopic to the identity of Y. Okay. So this was only the first condition. We need a second one. This condition just sort of gives us composition up to homotopy, and it gives us a notion of inverses. But now somehow we have sort of a slight problem, because I've been telling you equality in homotopy theory should be data. But now we have sort of two ways of identifying objects. One way is to talk about paths in C0, and the second way is to talk about isomorphisms between objects. So the second condition is called the completeness condition, and this will identify these two notions of equality. Okay. So we have this notion of isomorphism, and in particular, we can look at the subspace of C1 that consists of all the morphisms which are invertible. And the second condition that we need is a completeness condition, which says that the map from C0 to isomorphisms in C, which is this map, this map I that it wrote over there from C0 to C1. Let me denote it by sending X to the identity on X. We want this to be an homotopy equivalence. So in a certain sense, we are asking the identifications that we have using isomorphisms to be, just identities in our space C0. Yeah. Okay. So this is one possible model. There are maybe different models for affinity categories. But from now on, let me try to phrase everything in a sort of model independent way, in a way that doesn't really refer to any specific choice of model. Okay. So how does the theory of higher categories behave? Well, one important criterion that we need is that every ordinary category can be seen as higher category. I really want to think of infinity categories as sort of a generalization of ordinary categories. So I just want to write C again for this object. And then we can do a bunch of constructions. We can form the terminal infinity category. Which I will denote by star. And it has a universal property that every C has a functor into it. Any two functors are going to be naturally isomorphic to each other. There was an initial infinity category. Which I will denote by the empty set. And again, for any infinity category C, there's going to be a functor. And it's sort of unique up to isomorphism. So any other functor will be naturally isomorphic to it. We have notions of products and co-products. If we have an infinity category C and infinity category D, we can form the product and a functor into the product will correspond to a functor from T to C, together with a functor from T to D. Dually, we have co-products. Yeah, maybe so, the point where something maybe slightly new happens is for pullbacks. So given F from C to E and G from D to E, we get something which I will denote by the pullback, but it's sort of more like an homotopy pullback. So a functor from D into the pullback, but what should it be? So we are used to thinking of, pullbacks. You just have a map to C, you have a map to D, and then the diagram should commute. But we're doing homotopy theory. So the fact that the diagram commutes should really be data. It should be the data of a natural isomorphism between the composite, let's call this T and S. The composite F of T should be isomorphic to G and S. So it's sort of a high categorical universal property of the pullback. And then we have things like functor category. From CD, and it has a universal property that the functor into the functor category corresponds to just the functor out of the product.
Yes, one question from the chat, namely about the model. So, what are the functors actually? So, are these just maps of simplicial topological spaces? Or...
Yes, the maps. So the question was, what are the functors in the specific model? And they are just going to be natural transformations of simplicial objects in top.
Sorry, I think that there is one more question.
I think the question might be what the infinity category of infinity categories is in this model. So is this also just some complete Segal space? But yeah, I have asked for clarification.
Okay, so wait, what was the question?
So Is the in the model,
Yes.
complete Segal space model, is the infinity category of infinity categories itself a complete Segal space?
I mean, yes. I mean, it should be. But it's probably a bit tricky to describe it directly. But yeah, I mean, basically, I can, okay, so morally, okay. Let me tell you what sort of the interpretation from of the complete Segal spaces is from a model independent perspective. So given an infinity category C, so for every n, we get a poset, which I have already used before, but every poset we can think of it as a category. So I'm going to write it smaller or equal as an arrow. So I think of the poset bracket n as sort of the universal category, which has n+1 objects and it has n composable morphisms. So I can look at the functor category out of that into C, and this is sort of the category of all n composable morphisms. And now I want to sort of forget, I only want to look at this object, the objects of this. So I sort of, yeah, I didn't tell you this, I was kind of planning on telling you this, but this means take a subcategory that only consists of invertible morphisms. And this defines a functor from delta up into, okay, yeah, I should have maybe not made this remark because now I'm going to use things that I was going to talk about later. Anyway, like, yeah, it turns out that you can think of this as topological space, and this is sort of a model-independent description of the complete Segal space corresponding to the infinity category. But maybe I shouldn't say much more about it because otherwise it just gets confusing because I'm using things that I haven't defined yet. Okay, but yeah, something that is useful to take away from this discussion is, in particular, if we take n equals 1, we recover the notion of a morphism in C. Let's just define a morphism as a functor that's called f from this category 1, and then the source is evaluated at 0, and the target is evaluation at 1. So in particular, for every pair of objects x and y, we get something that we call the home space. So what should the home space be? Well, it should be a subcategory of the functor category. Like we have the category of all morphisms. It's just this functor category from this bracket 1 thing to C. And then we can evaluate at 0, and we can evaluate at 1. Here I got C times C. And then I want to impose that the source is x and the target is y. So I put here the object x comma y in this product. I'm only using things that satisfy these universal properties. I'm not using anything else. So the map into the product is just a pair x comma y. And then there is this pullback, which I'm going to denote by home x comma y. And now we can do a bunch of definitions we're used to. For example, we can define what fully faithful functors are. So the definition of functor f from C to D is called fully faithful, if the induced map from the home of C to the home of D, and this induced map just arises from the universal property of pullback. In the functors from this bracket 1 to C, I can compose it with F. So I can map this to the functor category from 1 into D by just composing with F. I mean, this is something that you can define using this universal property I stated. And then the target will be home. I mean, yeah, you can see that it lands precisely in this fiber. So by the universal property of pullbacks, you get this induced map. And then we ask this is an equivalence. I didn't define what equivalences are, but just the usual definition. You have a functor in the other direction, and both composites are naturally isomorphic to the identity map. And similarly, we have a definition of essentially surjective. So, definition, a functor f from C to B is called essentially surjective. If for all y in B, there is an object in the source such that the image is isomorphic to y. And now, from ordinary category theory, we know a functor is an equivalence precisely if and only if it is both fully faithful and essentially surjective. And it turns out that this theorem is still true for infinity categories. Yeah. So theorem. Functor f is an equivalence if and only if it's fully faithful and essentially surjective. And this theorem is sort of slightly more difficult to prove than for ordinary categories, but it's still true. Another theorem, which is very useful to know, is that given a natural transformation, okay, so what is a natural transformation? A natural transformation is a functor. It's just a morphism in the functor category. And then by currying and uncurrying, this is sort of the same as a functor from C to the morphism category of B. So a natural transformation is a natural isomorphism, so it's invertible in the functor category, if and only if it's pointwise invertible. In other words, for every object x in C, the induced map alpha x from fx to gx, so it's taking this perspective and just evaluating the object at x gives us a morphism in D from fx to gx is an isomorphism in D. Let's see, what do I want to discuss next? Yeah. Okay, so yeah, some more constructions. Maybe I will be a little bit brief. So for example, there's a notion of opposite category. And the main property of opposite category is that the home space in the opposite category is just the home space in C, but then with the sort of the target reversed. There is a notion of a subcategory. If you have a collection of morphisms which is closed under composition and contains all the identity maps of it's suitably closed under identity maps as well. We get a subcategory. And maybe the most relevant construction we can do is localization, also known as wire-count localization. And it means inverting a bunch of morphisms. But let me spell this one out in a bit more detail. So if we have an infinity category D, so if you have an infinity category C and a collection of morphisms, W and C, then we get a new infinity category called C W inverted, which comes equipped with a counter that's called L from C to C W inverse, which satisfies the property that any morphism in W over here is sent to an isomorphism in this infinity category, and it's universal with this property. So more precisely, it means that for every other infinity category D, composition with L induces a fully faithful counter Okay, so composition with L, it starts in the counter category of counters from this localization into D. And then if we pre-compose with L, we end up in the functor category from C to D. And the claim is that this is fully faithful, so we can recognize when a functor from C to D comes from a functor from the localization into D. And the image is precisely those functors that invert all the morphisms in W. So those functors have such that any morphism in C, which happens to be in this collection W, is sent to an isomorphism in D. This is, let me give you two examples of infinity categories that arise as localizations. Because it can happen that we start with a one category and we invert some morphisms in this universal way. And then it suddenly becomes a very interesting infinity category. That's one. Yeah. So yeah, two examples of localizations. The first one is the infinity category of spaces. The infinity category that we denote by SPC, sometimes it's also called just S in the literature. And what you do is you start with the ordinary category of topological spaces, and you look at all the weak homotopy equivalences. And you formally invert those. So this receives a functor from top that inverts all the weak homotopy equivalences in a universal way. And it turns out to be equivalent to take the CW complexes and just invert the ordinary homotopy equivalences. So this, because we are doing this inversion in the world of infinity categories, this now is an honest infinity category, so it has objects which are sort of CW complexes. The morphisms are just morphisms of CW complexes. But now it also contains homotopies between morphisms and homotopies between homotopies and so on and so forth. And this is sort of the most fundamental infinity category that there exists. It's sort of it plays the role in infinity categories that the category of sets plays in ordinary categories. Okay, the second example I want to give is for R, a ring, we have the derived infinity category. You obtain it from taking the category of chain complexes and inverting all the quasi-isos. All the quasi-isomorphisms, you formally invert those and you get another interesting infinity category in which you can do homological algebra. Okay, but okay, so the next thing I want to introduce very briefly is that there exists an infinity category of infinity categories. The objects of this infinity category are small infinity categories. The morphisms are functors. The homotopies between functors are the natural isomorphisms. And we can consider the full subcategory of cut infinity spanned by the infinity groupoids. And in fancy language today, they are also called anime. Those infinity categories and that all morphisms are invertible. And now there is an important theorem which is called the Grothendieck homotopy hypothesis. It relates these two infinity categories that I wrote down. So we have now this infinity category of spaces. It is sort of very topological. And then we have this very categorical infinity category of categories in which all the morphisms are invertible. And those turn out to be equivalent. So theorem, the functor pi infinity, maybe, yeah. For time reasons, let me not precisely write down how you can do it, but it's basically first take the simplicial nerve of the singular complex of your topological space, and then you can sort of realize it in your category anime. Maybe to be safe, I will write CW complex. So the functor pi infinity inverts all homotopy equivalences because this functor inverts all the homotopy equivalences. We get a functor from the localization. It's just a universal property. We can apply the universal property, and we get a functor from the infinity category of spaces to the infinity category of anime. And this is an equivalence. So maybe this sort of sheds a little bit light on why these spaces are like so relevant in the theory. They are sort of very fundamental objects. They appear in several different guises. Okay. And now the final thing I want to talk about today is limits and colimits in infinity categories. They sort of correspond to what is usually called homotopy limits and homotopy colimits. And sort of the upshot is because our infinity category theory has built in all these homotopies, we can really take the ordinary definition of limits and colimits, make sure that we write it in such a way that it still makes sense, and then that will be the correct definition of our limits and colimits in infinity categories.
There's a question in the chat about whether the definition of spaces and anima that you gave are the same size, or if they're different.
Yes, they are the same size. So the topological space, I really sort of mean small topological space, so it's a set of objects and so on. And here it's also small infinity groupoids, so they both live in the same universe. I see what you mean. Do I see what you mean? I think it's fine, but also, yeah, I mean, also the set theoretical issues are not super relevant because maybe you have to pass to a different Grothendieck universe. But I don't know. But I think it's fine. Let me know if there is something relevant. But yeah, okay. So in the last 5 minutes, let's define limits and colimits. So let's assume we have some functor from some infinity category I to some infinity category C. We want to think of I as some indexing category. So to define limits, we first have to talk about cones. The cone of F is an object X. And now we need, for every object in I, we need sort of a morphism from X to F of I, and they sort of need to satisfy a bunch of compatibilities. And if you think about it, the compatibilities we need are precisely the data of a natural transformation. from the constant functor on C. So just a functor from I to C, which first goes to the point and then goes from the point to C to F. Let's call this epsilon. And then we say that it is a limit cone if it's universal. So what does universal mean? It means that for every other object y in C, there is an equivalence between the home space in C from y to x and the space of natural transformations from the constant diagram on x to f. So this is the space of cones. How do I define this space? Well, I just define it as a certain home space in the functor category. So we have the functor category from I to C. It itself has a home space, and we can just look at homomorphisms in there from the constant functor on y to f. And this map is induced by first taking the morphism from y to C to x, and then sending it to the induced natural transformation from the constant functor on C to the constant functor, sorry, the constant functor on y to the constant functor on x. And now we can compose by the epsilon we are given. This defines a map from here to there. And we argue this is an equivalence. So if you think about it, this is really just the ordinary universal property of limits, just formulated in such a way that we don't need to talk about individual, just a reformulation of it. And if we invert all the directions, we get a notion of colimits. So let me end in the last 2 minutes by giving you some examples of limits and colimits. So example 1 is if I is just the empty category, then you can prove from the axioms that I wrote down that the functor category from the empty category into C happens to be equivalent to the terminal category. So on the right-hand side, we have the home space in the terminal category. This will just be contractible. So here we just get a point up to homotopy, up to equivalence. So the notion of limit that we get, the limit over I of f will just be a terminal object. In other words, the morphisms from y to x are contractible for all y. Similarly, if we take I to be the disjunct of 2 points, then you can prove, again using the universal property, that the functor category out of this I is just equivalent to 2 copies of C. And then if you look at what the right-hand side is, then that's precisely the universal property we want a product to be. So if f will now correspond to a collection of objects x0 and x1 inside this product, and then the limit of f is precisely the product of x0 and x1. That's our definition of the product, actually. And then maybe, yeah, I'm already over time. Maybe let me not go into too much details, but if you take I to be the indexing category, which has 3 objects and 2 morphisms like this, then you will get the notion of pullbacks, which we really want to think of as homotopy pullbacks, because the commutative diagrams in our infinity category contain the data of a homotopy. And maybe as a last example, we can take something that So we can take I, for example, to be the category BG for a finite group G. So it has one object, has G many morphisms. A functor F will now correspond to an object X in C together with the G action. And then the limit of F is often denoted by X to the power HG, and it's known as the homotopy fixed points. Okay, sorry for going a couple of minutes over time. I will end it here.
Okay, let us all think. Bastiaan,
Yes.
are there any questions?
Oh,
Yes, Zhao Ting, do you want to unmute?
Yeah. Yeah. So I remember in your definition of localization, you have no conditions on the collection of morphism stuff at all. Is it the case? Because I saw a lot of situations that people require like 2 out of 3 properties on the W. Yeah. Is it? Yeah. Can we define localization for a general collection of
you
W?
don't need it to be, yeah, you don't need any 2 out of 3 property. You can, in principle, just invert any class of morphisms, because what you can always do is take your collection of morphisms and close it up under composition. You can just say, take your morphisms. I'm gonna take a bigger W prime, which consists of all the composites, like the finite composites I can make with morphisms in W, and you will see that whenever a functor from C to D inverts, so given W, we can take this W prime, and if F from C to D inverts all the morphisms in W, it will automatically also invert all the morphisms in W prime.
W prime maybe the closure under 2 out of 3, or I mean under both.
Yeah, you can also do that. Let's do that even. Yeah. Oh wait. Yeah, exactly. So Benny just recommended that I should even close that one to 2 out of 3, because then it actually addresses your question. Yeah, exactly. Thanks for the. And then the point is that isomorphisms in D satisfy the 2 out of 3 property. This you can just prove. I mean, this is just a fact you can prove. And then you can prove that it follows that it inverts all the morphisms in W if and only if it inverts the morphisms in W prime. So yeah, the answer is it doesn't matter, but sometimes if you want to say something about this localization, it can be more convenient to have a collection of morphisms about which you know more. If it's closed out of 2 out of 3 property, and if it's closed under pullbacks, for example, you might have a chance of giving explicit descriptions of the home categories, for example. I mean, the home spaces. So yeah, the answer is in general, you can just form this localization, but sometimes you know more about it.
I see. Thank you.
Any more questions before we stop the recording? Okay.